Next, we're going to look at some computations using the second part of the fundamental theorem calculus. Now, in the last video, we discussed a little bit about what the second part means. Here, we're going to go through some computations. We're going to do 8, and then we're going to do another example after this. Evaluate each definite integral. So let's do them. Part A. I may wind up erasing these if I need board space. Part A. Integral from 1 to 3, x cubed minus 2x dx. Now, what does the second part of the fundamental theorem calculus say? Well, it says, remember, fundamental theorem calculus 2 says the definite integral from a to b equals capital F of b, the top end point, minus capital F a, the lower end point, where f is any antiderivative of lowercase f. So all we need here is an antiderivative of this function, and then we need to evaluate it at the endpoints and subtract. So let's do that. Well, to find an antiderivative, we can use our rules. We are going to introduce a little notation in this. And what does that mean, any antiderivative? Well, we'll see. Well, we'll see right now what we mean by any antiderivative. So right here, x cubed, an antiderivative of that, a quarter, x to the fourth. Negative 2x, what do you get? You get a half x squared, and then the 2's cancel, so you get minus x squared. Now, any antiderivative, there's an antiderivative. We could have added any number that we could say plus 1. There's an antiderivative. I'm going to choose the one where c equals 0 for convenience. So right here is an antiderivative. I'm going to choose the constant to be 0. The second part says we can use any antiderivative. We're evaluating from 1 to 3. So here's some notation to remind yourself that you still have to evaluate. I'm going to put this in parentheses, put a vertical line with a 1 at the bottom and a 3 at the top. And that's going to remind us to substitute 3 and then subtract what happens when you substitute 1. So first, the second part says equals capital F of b minus capital F of a. So capital F of 3 minus capital F of 1. And here's our capital F. Let x equal 3. What do we get? 81/4 minus 9. I'm going to throw this in parentheses here, just to make it clear exactly where f of b and f of a are. Minus, what happens when we evaluate 1? What do we get when we evaluate at 1? 1/4 minus 1. So now we just have to combine all these numbers. 81/4 minus 1/4 is 80/4, which is 20, and then you have negative 9, positive 1 makes a negative 8. So this one is 12. So any antiderivative, I chose the constant to be 0. What would happen if you chose the constant 1? Well, you get a quarter x to the fourth minus x squared plus 1, evaluated from 1 to 3. What happens when you substitute? Well, you'd get 81/4 minus 9. Then you get a plus 1. Then you get another plus 1. Notice that 1 and that other 1 cancel. So you could use the antiderivative where the constant of integration is 1. Or, you could let it be pi. I would recommend strongly against that. Just stick with letting the constant be 0. Because when the constant is 0, there's less to think about. B. Integral, where are we? Integral from 1 to 8 of the cube root of x with respect to x. Well, I'm going to write that as a fraction, as a power function. X to the 1/3 with respect to, how do we do x to the 1/3? Well, 1/3 plus 1 is 4/3. divide by 4/3, evaluate from 1 to 8. Now in all of these, at this step, I guess I didn't do it in part A, I like to check to be sure I did the right derivative, the right antiderivative, just by taking the derivative of this function. Derivative of this function, the 3/4, 4/3 cancel, so you get just x to the 1/3. You could, again, choose constant 1. Don't do that. Constant 0. Evaluate from 1 to 8. Well, we have that 3/4 there. I'm just going to factor that out. Equals 3/4. I'm going to factor out the 3/4 just so I don't have to write it twice. What's 8 to the 4/3? What's 8 to the 4th? What is it, 4,096, I think? 2 to the 12th? Well, what's the cube root of 4,096? I don't know. Well, I do know. But not because I know that. I know it because we can find the cube root of 8, which is 2, and then raise it to the 4th. 2 to the 4th is 16. Subtract what happens when you evaluate 1. Since we factored out the 3/4, we don't have to worry about the 3/4 in this next step. 1 to the 4/3 is 1. So you get 16 minus 1 times 3/4, which is 45 quarters. Part C. Integral pi to 2 pi of cosine. We need a function whose derivative is cosine. Do we know a function whose derivative is cosine? Yes, we do. The derivative of sine is cosine. We're evaluating from pi to 2 pi. So we need here sine of the top number minus sine of the bottom number. What's sine of 2 pi? Where's 2 pi? 2 pi is over here. The y value is 0. What's sine of pi? The y value is 0. So we get 0 minus 0, which is 0. D. Again, the constant of integration, choose to be 0. Make your lives easier. 0 to pi over 4. Yeah, maybe I should have done one with a negative. Yeah, well, whatever. Secant x tangent x. We need a function whose derivative is secant x tangent x. Well, the derivative of secant x is secant x tangent x. We're evaluating from 0 to pi over 4. And what do we get? Well, we get secant of pi over 4 minus secant of 0. What's secant of pi over 4? Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent, so root 2 over 1. What's secant of 0? Cosine of 0 is 1. 1 flipped around is still 1. So secant of 0 is 1. Next, part E. So earlier in this video I said we'd do one example after these 8. we will do 2 examples after these 8. E. Integral of 3 over x to the 4th. From 1 to 2. Why didn't I say 0 to 1? Well, we need the function to be continuous on the entire interval. That function is not continuous at 0. So I had to push the bounds of integration away from 0. How do we do this? Well, we have another power rule. Negative 4 plus 1, negative 3. 3 divided by negative 3, negative 1. So we get negative x to the negative 3rd from 1 to 2. I don't like evaluating with negative exponents. I'm just going to write that as negative 1 over x cubed from 1 to 2. And what do you get here? Evaluate at 2, negative 1/8. Subtract. What happens when you evaluate at 1? When you evaluate at 1, you get a negative 1. Subtract negative 1. I'm going to change part f, sorry. Make it e to the x plus 1. I don't think, yeah, the first 5, I don't think we had just a plus a constant. I guess in the last one we do. Well, whatever. E to the x plus 1. E to the x plus 1, how do we do this? Well, we do it piece by piece. A function whose derivative is e to the x is e to the x. A function whose derivative is 1, x. We're evaluating from, that's not a good 2. We're evaluating from 0 to 2. Substitute 2, you get what? E squared plus 2. Substitute 0, what do you get? E to the 0 is 1. Substitute 0, you get 1 plus 0. So you get e squared plus 1. If I didn't throw that plus 1 here, your answer would have just been e squared minus 1. Not just e squared. E squared minus 1. How about part G? Integral of 4 over x squared plus 1 dx. Why 4? Well, first I'm going to pull out that 4. Oh, I thought I stepped on something, but I didn't. We need a function whose derivative is 1 over x squared plus 1. Well, we have one. The derivative of the inverse tangent function is 1 over x squared plus 1. We need to evaluate from 0 to 1. So what do we get? You get that. This time I didn't factor out the 4. With that one with the 3/4 I did. This time I'm not going to. I mean, I could, but I just didn't. To show how this would look. We need an angle whose tangent is 1. The tangent of pi over 4 is 1 over 1, which is 1. we need an angle whose tangent is 0 and is within, what, quadrants 1 and 4, or the positive x-axis. The tangent of 0 is the sine of 0 over the cosine of 0, so the tangent is 0, 0 over 1, which is 0. So you get pi minus 0, which is pi. Eighth. H. Integral. The other time I said eighth, not h. This time I said h. 3 plus x root x. That's a mess. That's less of a mess. So eighth and h sound very similar. I never realized that. You go through 29 years, you'd think you'd notice that nice parallel between the numbers and letters. But nope. How do we do this? Well, we have a 3. A function whose derivative is 3. We can take 3x. What about x to the 3 halves? How do we do that? Well, we get x to the 5 halves with the power rule. 3 halves plus 1 is 5 halves. Divide by 5 halves. It's the same as multiplying by 2/5. So you get plus 2/5 x to the 5 halves, evaluating from 0 to 1. And putting a 0 in this one is convenient because it makes the future computation less tedious. What do we get when we evaluate at 1? You get 3 plus 2/5. What do you get when you evaluate at 0? You get 0 plus 0, which is 0. 3 is 15/5. So 3 plus 2/5 is 17/5. So the second part of fundamental theorem, these computations are immensely important, especially as you go on to Calc 2 and Calc 3. Calc 2 is, you know, about half of the semester is doing these computations and making them more complicated. But let's look at an application of these. Example. We'll do 2 examples here. Find each area. And that doesn't mean point at it on the board, that means find the number. A. What was the example I did in my notes? X squared plus 1. X squared plus 1. Was that the one we did in our... I don't know. No, I think it was x squared plus 3 in the area approximation. Yeah, let's do x squared plus 3. And in that video, I think we did 1 to 2. Yeah, whatever. Let's just make it x squared plus 1. Because I want to do it from 0 to 1. Part A, find that exact area. Part B, I'll put over here. Part B, find this exact area. Let's do pi to 2 pi. Of sine of x. How are we going to find that? Well, remember, the definite integral gives us this area. So this area equals, for part A, the definite integral, x squared plus 1, starting in this case at 0 and going to 1. So what do we get here? Well, we get a third. We need an antiderivative, third x cubed, plus x. We're evaluating from 0 to 1. Sometimes I don't write the parentheses around these, sometimes I do. When you evaluate at 1, you get a third plus 1. When you evaluate at 0, you get 0. So here, 4/3. Oh, okay. The answer in my notes is 14/3. Because I put a 2 there in my notes. How about this next one? Well, again, the definite integral gives that exact... yeah, okay. Find this area. I'm not going to ask one like this. This is to illustrate something else. This integral, remember, the definite integral gives the area using the approximation using rectangles. When I mentioned there'd be one problem after those 8, and then changed it to 2, I was going to do from 0 to pi. Then I realized it was the same as that, so I did this, and it's not what I wanted, but it'll illustrate what I want. And what do we get here? We need a function whose derivative is sine. The derivative of cosine is negative sine. So the derivative of negative cosine is sine. And here, I'm going to pull out this negative and this kind of factor out a negative 1. So you factor out a negative 1, cosine of the top minus cosine of the bottom. Cosine of 2 pi is 1. Cosine of negative pi is negative 1. So that gives negative 2. Why are those cosine values what they are? Cosine of 2 pi, the x value is 1. Cosine of negative pi, cosine of pi, negative 1. So you get 1 minus negative 1 plus 1. So that gives us negative 2. The directions here said find the area. Why does that give us a negative? Area is not negative. So this area is 2. Remember, the definite integral treats areas below the x-axis as negatives. Treats areas above the x-axis as positives. So here, now be careful with reading the directions. These directions did not say evaluate the definite integral. These directions said find the area. And we're using the definite integral to find each area. In this case, the definite integral gave it out exactly because it was always above the x-axis. In this case, we got a negative for our definite integral, so we did have to interpret that over here. Let's look at one more application. Actually, I'm going to make this the next thing a separate video. It'll be 5 minutes or something.